Prestige Worldwide, Inc. has been tasked with designing a major civil engineering project that links downtown San Diego with the Naval Air Station North Island in Coronado. There have been significant recent complaints from the public who live in Coronado of military traffic that cuts through their city to access the naval base, using the existing San Diego-Coronado Bay Bridge as the conduit from San Diego. The existing bridge will continue to serve the civilian community of Coronado. However, military personnel will be required to take the new route that links the city of San Diego to Nasny. Our team of experts analyzed several alternatives, a bridge, a tunnel, and a combination of the two. It was our primary goal to design a connection in a secure location where a security checkpoint could be constructed before entering the connection to protect military personnel from threats. This is our team. Roughly 80,000 people, civilians and military personnel alike, cross the Coronado Bay Bridge on any given workday. Of that number, an estimated 34.5 thousand of those are military personnel entering Nasny. The road behind me is 3rd Avenue, the main arterial into the base. Due to the security checkpoint on the base and the traffic signal at the intersection of 3rd and Orange, this vital artery backs up all the way onto the bridge, causing severe traffic congestion for the entire area. The level of service for this road operates at an LOS of F, where it should be operating at an LOS of C if the military personnel were off. This is the primary reason why a new connection must be built, to alleviate the congestion on the island and this quiet city back to its people. After examining all of the surrounding issues and the traffic concerns for several locations, our team has determined that a tunnel design would satisfy all the needs at the expense of a larger price tag. The tunnel will be roughly 15,000 linear feet and will be beginning at Washington Street, right here. And it's adjacent to the 5. It will then travel underneath the Lindbergh Field on the landing strip and will travel underneath the bay along this path and will come up parallel on Rogers Street at the intersection of 282 and Rogers Street. The Nasny cross-section will consist of 5 lanes and will be 89 feet wide and will have a type 60 concrete barrier in the center, 2-foot shoulder offsets with 3 lanes going to the base and 2 lanes coming from the base. There will also be an emergency egress of 3.5 feet on each side, and then there will be 4-foot walls on the outer edge. This is the one segment of the tunnel, and each segment will be roughly 300 to 500 feet long.
Geotechnical constraints of the proposed Nasny tunnel connection mainly arise from the geologic setting of Coronado Island. As you can see in this figure, several earthquake zones cross through Coronado Island at many locations. Specifically, there is the Spanish Bight segment of the Rose Canyon Fault running approximately just west of the tunnel location on the Nasny site, as well as an active fault zone that terminates approximately 200 feet south of the site, which is designated by the shaded area shown in the figure. Another geotechnical obstacle of the Nasny tunnel connection is the susceptibility of underlying soils to liquefaction on both the Nasny side as well as under Lindbergh Field shown in this figure by the yellow area. The soil data used for analysis was collected from two separate locations designated by the two yellow arrows pictured here. The bay soil was collected from the NASNY 13 site by means of several vibrocores and borings. The bay deposits varied from silty to clayey sands and poorly graded fine to coarse sand with abundant shell fragments. A summary of the NASNY 13 soil parameters can be seen in this table. The NASNY 64 soil data was collected by means of a cone penetration test sounding to a depth of 50 feet. The soil was typically poorly graded sand to silty sand, and a summary of the parameters used can be seen in this table and in the following chart. To account for the risk of liquefaction-induced settlement, analysis of different pile foundations were conducted to ensure the tunnel would not be destroyed due to a seismic event. The following images are different pile foundation designs considered, altering the diameter, length, and spacing of piles. A rough representation of the NASNY tunnel on a pile foundation is shown in this Google SketchUp drawing.
The purpose of the hydraulic design is to provide a dry tunnel. Apart from the obvious safety considerations, a dry tunnel has aesthetic value which is important to users. A leaking tunnel incites discomfort within users and therefore makes waterproofing and an adequate drainage system a high priority. The waterproofing system was implemented to prevent groundwater inflow into the tunnel. The general allowable groundwater infiltration for tunnels is 0.002 gallons per square foot per day. However, with an external watertight steel lining or membrane on the outside of the tunnel, it will prevent groundwater intrusion entirely. It will cover the entire tunnel perimeter and will be 1/4 of an inch thick and also comprised of galvanized steel for corrosion protection. It is important to monitor the steel membrane to ensure it maintains the minimum design thickness. The drainage system is located at the bottom of the tunnel roof and was designed to accommodate for a 100-year flood event. It collects and drains surface water, which is then conveyed to a natural discharge location. The specific location of concern that was studied was the long-term parking lot now resting on Lindbergh Field. This location is where the tunnel entrance leading to NASNY would begin. It is also upstream of the tunnel, therefore making it a key point of interest. The lowest point of our tunnel is located at station 106 plus 51 at an elevation of 71.7 feet below water surface level on the roadway. This point is closest to the NASNY side of San Diego Bay, and therefore our discharge point will be located there. Prior to discharge into the bay, the drainage water will go through a system of pumps and an oil water separator to preserve the environmental standards of San Diego Bay.
Structural design of the tunnel began initially with a rectangular reinforced concrete tunnel and mid-span supporting wall off-center to align with the roadway median. External loads were calculated to be greatest at station 62 plus 00 of the tunnel, the deepest point below soil before crossing the bay shore. Load resistance factor design was used for this tunnel. The worst case load combination was found to be the ASCE7 load combination 2, with dead and fluid loads multiplied by a factor of 1.2 and soil and live loads multiplied by a factor of 1.6. All external loads were applied to the rectangular tunnel in a structural analysis computer program. This yielded an unacceptably high bending moment in the tunnel top, even with the mid-span wall. Tunnel design began again with elliptical compression arches of varying peak heights and no mid-span supporting wall. This not only created a more open tunnel interior, but a large reduction in induced bending moment upon the tunnel top. An arch of 7 feet high reduced bending moment by 42.6% and was selected for further design as it provided the best compromise between bending moment reduction and a prohibitively large tunnel exterior height. With the compression arch size selected, a live load per Caltrans HS 2044 was applied on the roadway, in addition to the external hydrostatic, soil, and buoyancy loads. Soil support was modeled as springs, with a spring coefficient equivalent to the soil's modulus of subgrade reaction. This live load was moved until peak placement was found for maximum axial, shear, and bending moment of each tunnel member. The comprehensive analysis yielded the superior and cost-effective tunnel section shown here.
NASNY tunnel design will be an exceptionally intricate project, largely due to the connections needed to be made between the on-land section of the tunnel to the immersed tube section traveling through the bay floor. This connection poses an issue due to the necessity to have the final section of the landside tunnel to be partially immersed within the bay floor. To account for this, a temporary coffer dam will be constructed to allow for this partial immersion. This dam requires detailed structural analysis, which will need further review before the project can be put underway. The cross-section and dimensions of the tunnel will remain constant throughout the complete system. However, the means of construction for the different elements will vary slightly. Immersed tube tunnels can typically be found in two forms, either steel or concrete tunnels. Both types of tunnel perform the same functions after installation. However, the means of fabrication and immersion for each is where they differ. For purpose of this project, Prestige Worldwide proposes the use of the precast concrete tunnel sections. These concrete tunnels are usually precast completely on land using steel reinforcing rebar. The casting will take place in dry docks or specially built basins from where the tunnels will be floated to their final positions and lowered into the dredged trench. The construction process of an immersed tunnel consists of a number of significant processes. The initial stage of construction includes the excavation of an open trench within the bed of the body of water being crossed by means of dredging. While dredging is occurring, the individual tunnel elements of roughly 300 to 400 feet in length will be fabricated off-site, usually at a shipyard or in dry docks. These elements are fabricated from the bottom up, starting with the base, continuing on with the walls, and then finishing with the top of the structure. Each portion is constructed initially with outer forms and the rebar skeleton that will help reinforce the concrete. The concrete will then be poured and allowed to settle before additional portions of the tunnels are fabricated. In order to account for the need of an airtight connection between tunnel elements, the ends of each element are closed by bulkheads, which are set back a nominal distance from the end of the element. By setting the elements at a nominal distance, a small space is created at the ends of the adjoining sections that is filled with water and will require dewatering after the connections with the previous element is made. After fabrication and launching, the elements are towed into position over the excavated trench in their relative final positions. Once positioned and attached to a lowering device, ballast is placed in or on the element so that it can be lowered to its final position. For precast concrete tunnel elements, the typical ballast method used is that of a temporary water ballast. After placing the element in its position, connection is made between the newly placed element and the end face of the previously placed element or structure to which it is to be joined. Once the element is in its final position, butted up against the adjacent element, the water within the joint between two elements is pumped out. After locking fill is in place, the joint can be completed in the area made watertight. The landside portion of the Nasny Tunnel project will be constructed with identical tunnel elements as those used in the immersed tube section. However, the overall construction process differs slightly. Prestige Worldwide will utilize the common process known as the cut and cover method during the landside construction of the tunnel. In a cut and cover tunnel, the structure is built inside an excavation and covered over with backfill material when construction of the structure is complete. Two types of construction are employed to build cut and cover tunnels, bottom up and top down. For the purpose of this project, Prestige Worldwide will implement the bottom-up construction method, utilizing the open-cut excavation process. To account for slope stability of the excavation, the open-cut method slopes the sides of the excavation away from the trench to meet the adjacent existing ground line. Not only is this method more cost-effective, but it helps reduce the time frame for the project of the schedule as well.
The Nasny Tunnel facility will satisfy all of the needs of both the military and the public without disrupting the iconic San Diego skyline or air traffic from Lindbergh Field. This facility will be state-of-the-art, putting San Diego on the map as the best city, making it everyone's perfect city.
Look through the window, San Diego sun is rising. There'll be another beautiful day. When I first saw you, your beauty so surprising. I knew San Diego, I was here to stay. I found my perfect city, the finest city anywhere. The city is not only pretty, but like my best friend has so much to share. Surfing in the ocean, trolley locomotion, Chargers, Padres, Aztecs games, and Old Town's best margaritas, SeaWorld's playful dolphins, Shamu in his office, organ concert, art museum, zoo, oh, walk on the beach, that's the city where I will stay. My perfect city, December or May.